guys are not binomial trees anymore. You need to argue something.
Sir.
Okay. Can see them there? Okay, you can slide the board from here. Okay, we will wrap up Fibonacci heaps today. So can you hear me?
Yes, sir.
Okay, good. So we almost completed last time. So I'll just revise and get on with one little part which we left. So a Fibonacci heap is a collection of trees. So you have like this. And each node has a value and each tree is arranged, the values are arranged in min heap order. In addition, I'll have a pointer to the root containing min. So if this is a root that contains a min, I'll store that. The insert operation just will create, so I want to insert a new node. I will create a node, a single node with one value, add it to this collection. That's it. Okay, so that X is added. And I will put a charge of 1 unit on the tree. So the invariant I am maintaining is that every tree has a charge in its root, because the delete min operation will do some consolidation and it's going to use up all this charge to do all these merges. So the amortized cost of an insert is a constant because it just needs to pay for creation of this node and it needs whatever charge required, which is, we're going to call it 1 unit, to put on the tree. Delete min operation will delete the root that contains the min. So maybe it's one of this node. It will delete it, and then it has all these subtrees. It will consolidate all these subtrees with the other trees in the collection. What does consolidate mean? I'm going to go through the trees and merge 2 roots with the same degree. So here is where all the postponed cleanup action is happening, where whenever you have 2 nodes, 2 roots, 2 trees where the roots are the same degree, I'm going to merge them. What do I mean by merge them? I make one the child of the other. The min heap property tells me which one I should make the child of the other. The larger one becomes the child of the smaller one. Okay, so that is done in this consolidate step, so that at the end of it we have at most 1 root for any degree, and we will also update the min value. The amortized cost, we argued, is that how much charge the delete min operation did come with? Well, every tree in the original collection has a charge. That means somebody already paid for it, so you can use that to do the merging. But my child subtrees, they don't have charge, so I bring that cost to merge them. So the time amortized cost is my degree of how many children do I have. And at the end of it, I also want to maintain the invariant that every node, every tree has a charge in its root. So that can be degree many, max degree many trees at the end. So I'm going to put 1 charge on that. So whatever that unit is, so I will have amortized cost is order maximum degree of a node. And we will argue that is the only thing which I left last time, is the maximum degree is logarithmic in the number of nodes in the tree. And decrease key operation does the following. So what is decrease key operation? I want to change some, right? Change x to y. So if y is more than x, then something wrong. So because I'm allowed to only decrease the value. So the new value is more than x, just don't do anything. Otherwise, if parent of x's value, so I'm just going to refer to the parent node and the value, hopefully there is no confusion. The parent of this node is less than y, we are done. You don't have to do anything because I am still satisfying min heap property. Yeah. Right? Because I am, here is a node, its value is changed to y, and if the parent is smaller than itself, this guy, the new y, then its min heap property is satisfied, because down below you don't have to worry about, even x was smaller than all its children, it was a min heap. Now you decreased it even further, it will still satisfy the min heap. Okay. So if this happens, you're done. Otherwise, we don't want to go up the tree and do all that, because that's going to take log n time. So what we are going to do is the following. Cut the subtree rooted at x. Add it to the collection. Put a charge of 1 unit. Okay, so I have this tree which is x, which has got changed to y, and I have something here. This turns out to be bigger than or smaller than its parent, so I will cut this subtree, add it to my collection, and put a charge of 1 unit. Okay? But to avoid arbitrary cuts to any subtree, I want to do it a little more carefully. So one more step we'll do. Let's call this cascading cut. Okay? This is another subroutine. I'll explain what it does. What does it do? So now, okay, so what happened is, here is my tree, and here is this node which got changed to y, and this has been cut, and I created a new node here, new subtree with a charge there. Now I look at its parent of this node. I want to make sure that nobody loses more than one child. Okay, so we bring in this notion of mark, right? So initially every node is unmarked, so this cascading cut. So let's say with this parameter x, which is this root of this subtree, if parent of x is unmarked, mark it, and that's it, we're done. So initially everybody is unmarked. So my parent is unmarked means that I am the first child being lost. So that's fine. I marked my parent saying, okay, I've lost a child. What if the parent was already marked, right? Then this is the second child being lost. I have already cut it x, so there was maybe some other subtree which was removed. This is also removed now, I have done that. So now I am going to take the subtree rooted at the parent and cut it. Okay, so parent may have a lot of other things going on, right? Else, cut the subtree rooted at parent of x. So cut means this, and I will cut it, create a new tree, put a charge on it, and recursively cascading cut. Right, so this is a recursive call. What will it do? It will go and check whether the parent's parent is unmarked. If it is unmarked, it will mark it and stop. If it is marked, then it will cut that also and add it to the child and continue. Right? When does this whole process stop? Either you reach an unmarked parent, then you mark and stop, or you reach the root, in which case you just stop. Right? So I should say while parent non-empty. Parent is not, that means I've reached the root, right? So clearly the worst case for decreased key can be pretty bad. Right? Could be as bad as the height of the tree, because it can create a cascading cut. But we again argued the last time, amortized cost I'm going to say it's 4, whatever that 4 unit, right? When I say 1 unit, if you say the merging will actually take cost 2, then you multiply all of this by 2. So that is my one measure of 1 unit, right? The charge is really used to do this merging. Okay, so now I claim that this it's okay if a decreased key operation may actually require a lot of cascading all the way, but still there is enough charge on the tree to pay for them. So it's enough if I come with 4 units. Why? What do I do? So I will, if I am the first child, so I will cut it, pay 1 unit for cutting it, 1 unit charge, and 2 I give it to my parent. Okay. Later on, if the parent loses another child, it will get 2 more from that child. So it has gotten 4 to cut itself, right? Because it's recursively, 4 units is enough. So it will cut. So every marked node will have 2 units at all the time. Okay, so the invariant here every marked node. This marking is because of all this cutting has 2 units of charge. So if you want to argue the whole thing by a potential argument, the potential of the data structure is number of trees, because every tree has 1 unit, plus 2 into marked. Okay, so now all I have to argue, because of this careful choice of this cuts, that I never allow more than 2 cuts to any node. Right? I allow 1 cut and maybe 1 more cut, and then I will cut myself and go somewhere else. Right? Because of that, this degree of any node on a tree on n nodes will never be, it will be logarithmic, is what we all say. And this will bring in this, why we are calling it Fibonacci heap. So the claim, max degree of any node more precisely log n to the base phi, where phi is this golden ratio. Which is roughly 1.618. Any node in a tree on n nodes if I allow arbitrary cuts, I cannot say this, because I could, have a tree like this, because this lost all its children, this lost all its children, all of this, and then I have only 6 nodes here, but its degree is 5, closer to linear than logarithmic. Okay. And the way we will show this is by saying, if a node X has degree k, number of nodes in the subtree rooted at X as degree has at least phi equal to k. This is what we'll show. So to show that, first, so this is a goal. So let's say, so now all I'm saying is look at, these operations are happening, right? Insert, decrease key, delete min, they're all happening in all kinds of sequence of things. And at any point now I go take a snapshot and look at one tree. And let's say, let X be a node in one of these trees.
Sir?
Yeah?
Sir, we are not able to write the whole thing. Can we zoom out from the screen or something?
Okay.
So because the camera shifts again and again and
Full board over. Is that better? Yeah, so today we are working on some manual systems, so there may be some hiccups, but is this better? You can see the board? And let y1, y2, yk be its children in order in which they became child of X. Okay. So these operations are happening, and I look at one timestamp, look at one tree, and have a root. It may not even be a root, it could be any node in the one of the trees, and its degree is k. And let's say I just go back and say who got attached to X first among its children. Y1 got attached to it, and then Y2, and then YK. Right? Maybe there were more nodes which got cut later on. That's okay. This is the current set of children of X. Right? I'm going to look at them in the order in which they got attached to X. Okay? Then the claim is degree of y1 is greater than or equal to 0, and degree of yi is greater than or equal to I minus 2. Okay? This is the claim. Degree of y1 is greater than or equal to 0. Sure, no problem. I'm not saying much here. Okay? But look at y2. It became a child of X. How did it become a child of X? Which operation made this a child of X? Just think about the operations we are doing. Insert or decrease key or delete min or some consolidate or whatever. Delete min. Right? That is the only operation which makes something a child of the other thing. So why did y2 become a child of X? What was y2's degree at that time? It must have been the same as the degree of X at that time, right? Because that's why did you merge? You merged two roots with the same degree, right? So y2 at that time, when it became a child of X, its degree must have been at least 1. Doesn't make sense to say. Okay, I think I want to say y0, y1, yk minus 1. No, let's take this. Degree of y2 greater than or equal to 0, and let's say this from I equal to 3 to k. So degree of y1 greater than or equal to 0, y2 greater than or equal to 0, so I'm not saying much. But if you look at y3, its degree at the time when it became a child of X must be at least 2, because y1 and y2 must have been there, because I'm considering them in the order in which they became child of x. So its degree must have been at least 2, and it might have lost one child. Now, okay, so I really want to see the minus 1. Yeah, its degree at that time when it became a child of x must have been at least 2, because y1, y2 were there. Maybe there were more things also which got lost now. So its degree must have been at least 2, and now it might have lost one child because of the decrease key operation. And we don't allow it to lose more than one child, because if it had lost more than one child, this guy would not even be here. It would be somewhere else. So its degree now would be at least I minus 1, and this is true for every node, right? yi must have degree at least I at the time when it got joined, or I minus, sorry, its degree, yeah. So yi must have degree at least I minus 1 at the time, because there are I minus 1 guys before it, and now it might have lost 1. So its degree is currently at least I minus 2. This is the crucial lemma. This is where we use the fact that we never allow more than one cut, and then everything else will follow. Okay. So now so this is the proof of this lemma. The next lemma I'm going to say is let Si be the number of nodes in a tree with the degree I. Tree has degree I, meaning the root has degree I. Then Si is greater than or equal to one plus, so 2 plus I equal to 2 to k S I minus 2. Okay, this follows from this earlier lemma. So all I'm saying is I have a node with degree k. Okay, I want to count the minimum number of nodes in this entire subtree. Okay, now I'm looking at it from the basis of the degree. Suppose its degree is k, and suppose any tree with a root having degree k, suppose the minimum number of nodes is some sk. Okay, just a symbol. Then by induction, what is sk? Sk is at least 1 to count for the root, plus 1 to count for this node, so that's 2, plus the minimum. So now I already know a lower bound for its degree from here. So minimum number of nodes in such a tree with degree I minus 2, which will be Si minus 2. So from here, I know that this guy has degree, so any yi has degree at least I minus 2. And so such a subtree will have Si minus 2 nodes. Just S's definition is that. Si is the minimum number of nodes in any subtree with degree I. So the number of nodes, so this is 1, I'm counting this is 1 plus 1, 2, that is this 2. Then from here onwards, 2 to k, the number of nodes here would be whatever its degree, which is at least I minus 2, so S I minus 2. This is it, okay? So now you bring in Fibonacci numbers and say that Fibonacci numbers actually satisfy this condition and everything else will follow these. So eventually, yeah, so this is, in fact, more precisely, we will say, because at least k plus 2 Fibonacci number, and that is greater than or equal to 5. So let's now refresh our memory on Fibonacci numbers. So what is the convention I want to use? F of 0 is 0. Okay, so then turns out you can say you may or may not have seen this property of Fibonacci numbers. You can prove this by induction. Go up to k and add 1, what you get is k plus 2. Right? And k is 0, f2 is 1, and this is 0. So at least true for k equal to 2, or k equal to 0. It's a base case. Assume it's true for up to some k, and if you want to try for k equal to some I plus 1, assume true up to I. Then f I plus 3, right? And k is I plus 1, k plus 2 is this. By definition, this is f I plus 2 plus f I plus 1.
So the index on summation is I and inside is k. I don't.
Yep. Okay, so by induction hypothesis, when I put k equal to I, this is equal to 1 plus summation 0 to I f of I. This whole thing. And then you add fi plus 1. So this is 1 plus summation 0 to I plus 1 fi. That's what we wanted to prove it. Okay, so proof by induction. Yeah, and another claim is that Sk, which I am looking, is greater than or equal to Fk plus 2. Okay, so the next claim. And why is this? Because, we already shown Sk is this. So let me write this as 2 plus summation I equal to 0 to k minus 2 Si. And if you assume by induction hypothesis that Si is greater than or equal to Fi plus 2, this is greater than or equal to 2. So this goes from F2 to Fk. some calculations. Basically, we have that fk plus 2 is 1 plus going from 0 to k fk, and it just falls in that this is the number we are interested in, right? You have a node whose root has degree k. What is the minimum number of nodes it will have, right? And I want to show that that number is some exponential in k. That's all I want to show. That will show that the degree would be logarithmic in n, right? That the number of nodes in the tree, if the degree is k, the number of nodes would be exponential in the degree. Then, if there are n nodes, the degree would be logarithmic in n. Okay, so there will be lots of nodes. That's what's true in complete binary tree and all that, but because we have done all kinds of cuts, we want to make sure that it is still true and that is true. Okay. Instead of log n to the base 2, you have log n to the base something smaller. That's the only difference. Okay, so this is the crucial lemma. Since we are not doing arbitrary cuts, the degrees still remain very large, and hence the number of nodes will remain large. That's the idea. Okay, and independently, one can show that the k plus or kth Fibonacci number. Okay, let's try and show the next thing. Finally, okay, this is the last piece. I mean, you probably have seen it. You know how these Fibonacci numbers grow. So all it's saying is that this, you can again prove this by induction. Check for initial values. Right? What is y? F0 is 0, which is greater than or equal to. Yeah, so actually what I want to say is that k is greater than or equal to 5k minus 2. Sure. Okay, this will be less than 1 maybe. No. Or let's just try and show this for k going from 0. Okay. I care only about f2. f2 is 1, which is greater than or equal to. No, f2 is not 1. F2 is 1.
K is 2, power is 2.
And I want to show, yeah, phi to the power 0, that's 1. Yes, exactly. Right? K is 0. So I assume it's f3 is 2, which is greater than or equal to 5. So assume it's true for smaller values of k, then I have fk equal to, or fk plus 2 equal to fk plus fk plus 1, and this is greater than or equal to phi of k minus 2 plus phi of k minus 1, which is phi of k minus 2 into 1 plus 5. Now phi remember the Fibonacci numbers, the generating function, if you write the equation, it satisfies x plus 1 is equal to x square. So this is actually because 1 plus 5 is interestingly equal to phi. Okay, net, here is the whole summary that because of the way we are cutting down nodes, if the degree of a node is high, all its children will also have degree high. That's it. And hence, the number of nodes would be exponential in the degree, and hence, the degree is at most logarithmic in the number of nodes. Okay, that's the end of Fibonacci heaps, and so the main thing compared to binary heap is that we have decrease key and constant amortized time, and delete min is the order log n amortized. Insert is constant. Okay, so the worst case for delete min could be log n, or even more actually. Because if you have all these trees hanging around that may be as many as n trees or something, you may have to do consolidation. So the worst case can be bad, but the amortized time is logarithmic, and here it's, and we already saw why amortized time is useful, because in an algorithm like Dijkstra's or minimum spanning tree algorithms, we really are doing a sequence of operations, and so we don't care so much about worst case. Okay, I should also point out that the implementation details are pretty messy. We quietly did not talk about them because you have this collection of trees, and so you have to make sure the roots are all linked together, the children are all linked together, and various other things. But there have been alternative versions of Fibonacci heaps with the same kind of performance. It keeps coming up. So even now you'll see some research papers talking about alternative versions which achieve the same kind of running time. So
Simpler.
they claim simpler, but arguably. So if somebody is interested, I can point out some papers to read. Okay, so that's
So,
something there. Yeah.
One question there. Now, we were discussing the visualizing the degree of yi is greater than equal to I minus 2. So you said like so I minus 1 previous node. So that is I minus 1, and you said one more decrease key operation.
No, they are looking at a snapshot of the tree at any point and see what, and this is the tree, right? Now we look at them in the order in which they have been became a child of attached to x, right? So if you look at yi, at that time, not now, at that time when I was attached to x, its degree must have been at least I minus 1, because the consolidate operation will merge things only if the degrees are same. So since these nodes are still there, they must have been there also at that time, because we are looking at them in that order. They are here and they were there. Maybe there were more things here. We don't know. They got cut. So its degree at that time, and this became, or at least I minus 1. And so this guy's degree must have been at least I minus 1. But later, so this is at that time. But later on, it might have lost one child. So its degree would be at least I minus 2 now. Okay, good. That's it on priority queue. I want to just talk about another data structure that also comes from minimum spanning tree algorithm. So let's get there. Okay. So let you recall Kruskal's minimum spanning tree algorithm. Anybody remembers how it works? So the two popular minimum spanning tree algorithms are one due to Prim and the other due to Kruskal. Okay, how does it work?
So it grows the forests actually, the collection of trees. So what is assumed like, so you pick one edge, or initially you started with the isolated vertices. So initially the collection of forest is there. So you choose the minimum edge weight there. So by doing this, you actually join those two trees actually.
Okay.
So and it grows like that, so provided that no cycle.
Yeah. So we are going to consider edges in increasing order of their weights, right? Minimal spanning tree algorithm problem comes with a graph where every edge has a weight. So we will look at edges in increasing order of the weight. So it's convenient to sort edges by their weight. Right? Let's call this E1, E2, EM. After I have done this sorting, so E1 is less than or equal to E2 is less than or equal to EM, and we're going to consider them in this order. And so my goal is to collect a bunch of edges, right? The solution I'm going to consider. So first I will include E1. E1 is the smallest weight edge. It's safe to include it in my solution. And then it works like this for I going from 2 to M. If EI, so when do I add EI to my collection? So I'm looking at edges in increasing order of their weights. So I look at the next smallest weight. I'm going to add it to my collection F.
When it doesn't create a cycle.
Right. EI does not form a cycle. With edges of F. This is the entire algorithm, right? At a high level. I mean, we need to think about how do I implement this? That's what I was getting into now. But this is a whole algorithm. Just look at the edges in increasing order of their weights. Take the next edge. As long as it does not form a cycle with whatever I've collected, add it to my collection. Right. So the key thing is now, what kind of data structure do I want to maintain so that this step becomes easy, right? So at any point of time, what do I have in F? So F will have edges like this, right? So at any point of time, this will be my F. It's a collection of trees, right? And whenever I have, so let's call this EI edge is some XY. So when does it form a cycle? When does it not form a cycle? So EI is the edge X comma Y.
When both are in the same component or a tree,
Then
it forms a cycle.
it forms a cycle. So I can rewrite this whole thing as so let EI equal to XY. If X and Y are in different components of F, then I add EI to F, right? So we just moved one more step closer to implementation, and the problem now boils down to, I have this edge, more precisely I have 2 points. I want to know whether they are in the same component or in different components. So what do I want to store? What is my object which I want to store?
There must be some representation of the component.
Representation of the components, right? So I just represent each component somehow. Okay. One more step. Note that even the edges in the component don't really matter for me. What do I want to store? The vertex set of the components, right? That, I mean, edges are important because finally I have to output them, that's okay. But for this query, all I care is the set of vertices in each component, so that when the edge comes, I just go and say, okay, these two endpoints, are they in the same set or in different sets, right? So the next step of the implementation is, we are going to so what is the initial, so let's even make this empty for all you care, and I equal to 1 to n. So what will be the vertex set of the components when I start off? Okay, so what are the components when I start off? Initially,
Big whole entire vertex.
not really.
No, nothing.
No edge has been picked up. So what are my connected components? See, each individual vertex is a component by itself, right? Each individual vertex. So my component set, so let's now write C equal to 1, 2, let's say my vertex set is n. These are my sets, right? Let's say component 1, component 2, component n. For I equal to 1 to m, let ei equal to xy. If x and y are not in the same Ci, then f is equal to f union ei. What else I have to do?
So x and y, they will be in separate sets union.
Yeah, so whatever, so now my collection C will change to merge components containing x and the component containing y. Since they are different components, so now my data structure is f is the output, the set of edges I'm going to collect an output, and I maintain my components as a collection of sets. Initially they are all singletons. When an edge comes, I somehow check, are they in the same set or different sets? If they are in the same set, I don't add it at all. They are in different sets, I add ei to my collection and merge those two sets containing, the one set containing x and the other set containing y. Right? You had a question? Got answered?
Yeah, somehow you answered, like you have to find that. You have to
Yeah. So now let's see what is the data structure problem? Let's write down this data structure problem. The data structure problem is typically you want to maintain some set of objects and support some set of queries. Right? That's all. Right? So here I want to maintain a collection of sets. That's my object now. Right? I want to collect collection of these sets. In fact, they are disjoint sets. They are disjoint collection of subsets of 1 to n. And the queries I want to support, given x, I want to find the set containing x. Right? Every element is in some set. So, in particular, an x comes, I want to just somehow magically figure out which set it is there. And y comes, I want to know if they are in different sets, I can figure out. And what is the other query? Merge query. Right? Do a replace two sets by their union. That's my problem now, right? And whatever, so this How many unions does this minimum spanning tree algorithm does? And how many,
N minus 1,
okay, why?
because the edges has to be minus 1.
Right. Every time you do a union, you collect an edge. And finally, you are computing a spanning tree, assuming the graph is connected. So it will do n minus 1 union operation. And how many times it's going to ask this same set query? I mean, are these two elements in the same set? How many times I'm going to ask that? Well, for every edge, right? See, this is useful because now if I want to improve the if you want to calculate, improve the runtime, you have a goal of, what are the queries? If I'm after a particular runtime, which query is happening more often than the other, so you can focus your attention on the query that's happening more often. I'm going to focus reducing the runtime. So that's the kind of a goal. Right? So it's useful to know this. Now here's our problem. Let me start with a very simple data structure, and then we'll build slowly. Okay. So my data structure is I just have one array. Okay, so then just one array. So now, one thing which we did not really talk about is how are these sets represented? You can give a label for each set. This is set number 1, 2, 3 up to n. Gradually if you do more unions, the number of sets will come down, but that's okay. Or you can just use one of the elements in the set as a representative, because these sets are disjoint. You can just use one representative, unique representative set, so that if you want to know whether they are same set, or if the representatives are same. So there are many ways to represent this. So initially they are all singletons. So I'll just pick one element. So my S of I would be I, right? Because ith set contains element I. But as I move on, I pick one of the sets, change the label.
Finding will be just order of 1, huh?
Yeah, okay, so this is my structure, then find, right? Finding will be how much time? Order of 1, because if given an x, I just go to the array and figure out what it is. But union would be
again it's
Hmm?
order of 1,
order 1.
because you just have to
Remember, at any intermediate stages, I have no idea what the sets are and how big they are. Initially, they are all singletons.
but why we are to worry, like we just have to merge them you just add them and make one representative, like two big sets, two
But
big
you have to
array you
make the
have.
representative change in all the
I
other
am
places.
putting it in
It's
an array,
contiguous.
contiguous.
You have to make the representative change. Suppose, let's see.
So it's like 1, 2, 3, and they are all have the representative on each name.
Everybody has its own representative, but no, at the time you are merging two.
So let's say this is my collection, right? This is my disjoint collection of sets from 1, 2, 3, 8, right? So my S array would be like this. S of 1 is, so I'm going to call this set number 1, set number 2, set number 3, set number 4. Okay, some label, doesn't matter what it is, as long as I am consistent. So 2 is in set number 3, 3 is in set number 4, 4 is in set number 1, 5 is in set number 4, 6 is in set number 2, 7 is in set number 1, 8 is in set number 3, right now my starting data structure is just this array. Now if somebody gives me a value between 1 and 8 and ask me which set it belongs to, I just go to S of I. So in particular, if you give me two elements and I want to know whether they belong to the same set, S of X, S of Y, and compare whether they are the same, the labels are same, right? Now when I want to do a union, I might just do union set containing 4 and set containing 3, or no, let's say I want to do a union of sets 1 and 3. This is set 1, not element 1, it's set 3. Okay? So then what do I have to do? I have to go to this array, change all the 1s to 3 or change all the 3s to 1. Right? That's all I have to do. That means that these two sets are merged. But it could be order n because A, you have to find who are all 1s.
Maybe displaced. Maybe displaced, like not. You have to go through the entire.
Right. So how can we speed up things? First of all, should I change all the 1s to 3 or all the 3s to 1 in this case?
It's fine.
I mean, as a heuristic.
Okay.
Change this,
Keep the lower number.
change the smaller set numbers labels, right? But how do I find out which is smaller, bigger? So let's keep some more stuff, right? Let's do, can you keep an array size? In this case, 1, 2, 3, 4, which says the size of 1, set number 1 is 3, set number 2 is 1, set number 3 is 3. So now, if you want to merge set 1 and 3, you will go to the sizes and say, okay, set 3 has smaller elements, so change all the 3's to 1. If I can find the 3's faster, right? So let's create a linked list here. So maybe store the sets in a linked list, so you don't have to scan the entire array to scan. So I can, right? Who's the next element of 1 here? That's in location 4. Next element of 1 is in location 7, and this will be like a nil pointer. Right? I could store this. This is a, so that means essentially I'm doing this. And 3 will be linked like this. 2 there is nil pointer, and 4 will be linked like this. If I store the next and the size and this S array, the find cost doesn't change still, because you just go to that S of X and you will get that in constant time. But now if I want to merge two sets, you can spend time proportional to
The set size. The smaller set size.
the smaller set size, right? So find merge
In W, you can merge it constant.
I mean,
You need to change the label.
you need
For that, I think you need to go.
to change the labels.
So
Right?
for that
You
you
need
need
to change the labels.
Go by the
So you
names.
have to touch one set completely at least. Okay. But I mean, even this is not completely obvious. There are some details, right? So let's say I want to now merge two sets, sets 1 and 3. What do I do first?
So you compare the size of the set one.
Compare the sets, and I figured out that set number 3 is a smaller size. So I'm going to change all the 2's to 3.
But you need to know which
So,
starting point of that list of
Sorry, 1 and 3. So I'm going to change all the 3's to 1. Right? Okay, you need to know the
starting point.
of set 3. So this linked list is not complete. So let's also have a first pointer which tells you for each set. Maybe I should write here. Where is it? So what is the size and where is its first
First
element? So So I go to the first element, then I am in good shape, right? So I can go to the first element of the set, change it, follow through next pointer,
Look at the nil.
nil pointer, and do that, right?
And then also update all these.
There are more things to be updated, right? You have to update the size.
Size.
So when you merge two sets, one set size becomes the sum of the other two, the other set becomes 0. There is no element there. You also have to change some nil pointers, right? Because the last of one will become now the first of the other. Two sets have changed. So there are all these little bookkeeping details you need to do. So with all that, I claim we can support find in constant time. The worst case, merge will be when you want to merge two sets, their set size, smaller set size, right? But this could still be order n, because you may be merging two sets of size n by 2, n by 2 or something like that, okay? But here's a nice claim. What are we doing on time? Close, okay, let me write down this claim. I can actually, there's one line proof as well. Or maybe you can think about it, we can continue next time. So what is my claim? That just with this data structure, so far it's very simple. Just an array, I've built a little bit more, I've sized, and I kept each set in a linked list. That's all. Then I claim starting with n singletons, if you do, how many unions you said we will do at most? N minus 1, right? So each union in the worst case could be order n. But this is not going to happen very often, because if I'm starting with singletons, to get to larger sized set, you need to do a lot of unions to get there. Lot of small unions, right? So the claim is that the amortized cost is log n, which means this total cost for these n unions is not n square but n log n. Okay. So I mean, it's important that I'm actually doing smaller set size first, because I'll give you an example where, suppose, okay, so my set sizes are 1, 2, 3, 4 up to n. These are all singletons, right? I start with these kind of singletons. And suppose I am actually spending time proportional to the larger set size for merging. Okay, I merge these two. How much time I will spend? Well, both set sizes are 1, so let's say 1 unit. Now I merge with this union, I merge with this. How much cost would I spend? 2. Because the larger set size is this, right? I merge this. No, I'm not doing this. I want to say that to prove this log n, it is critical that I'm spending smaller, because if I do larger, I'll show you it's not n log n, it's n square. You could see this happening, right? Because now when I want to merge this with this, if you spend time proportional to the larger, it's 2. Now I have this 3 element set, merge with this, you're going to spend time 3, 4, and it's going to be n square. But if you are spending time proportional to the smaller set size, so this is exactly saying the amortized complexity of the union is log n. Even though the worst case can be n, the amortized complexity is log n. So I'll let you think about it. We'll start with this next time and continue. Okay, so think about the proof of this. We'll start with it.